All right. Hi, everybody. I'm here, live. This is Skip Elsheimer. Welcome to the AV Geeks Lunchtime Show. Hi, everybody. Where I forgot to mute my computer. Anyways, hope everybody had a great weekend. Good Father's Day for those who observe. Last week was brutal. A lot of schlepping films. All of us kind of teamed up, myself and my assistants, and we got a bunch of stuff done. I don't have pictures for you yet. What I was going to do is go around to all the storage units, all 7 of them, and get images so you could see how many films we have and the price of collecting physical media. It is not fun. Anyways, somebody had a question. Where was it? As a retired librarian, I have a question about how you archive your films. Are they grouped by subject, film, or by film company, etc.? They are by size and by letter in most cases. What we did is we realized the most efficient way for shelving was to combine like-sized films based on the cans, and then what we would do is put them by letter, not alphabetical within the letter, but all the A's that are 800-foot cans would go together. All of the B's that were 400 feet would go together, etc. That, I think, is the most efficient way. It doesn't easily lend itself to, I don't know, you spend a lot of time alphabetizing amongst letters. And I'm going to try to figure out a new way to do that when the films come back. After we do renovation work on the basement, we're going to figure out how to efficiently put stuff back. So there you go. So that first film that we watched, because that's what we do, is we watch 16mm films at the AV Geeks Lunchtime streaming show. And that was some raw footage from Cornet, Mass, and Weight. Some beautiful, beautiful footage of bowling balls. Big fan. Now we're going to watch a mediocre colored film called Birds in Their Homes. Enjoy.
It's a robin. Follow her flight and you can find her home in a tree. See the robin on the nest? This is one of many nests that you can find. Of course, you have to know where to look. Look high in a tree. There's the nest of a horned owl. Look low in a bush. There's the nest of a song sparrow. Bird homes are made of many different materials. The yellow warbler uses bits of grass for building, along with hair, pieces of cloth, and any other soft materials she can find. She uses her body to shape her home, making it into a good, secure place to lay eggs and raise her young. The nest will help protect the young warblers until they're old enough to care for themselves. In this tree, we can see a bird home of most unusual design, built by a Baltimore oriole. This is a hanging nest, attached to the ends of branches by long strands of grass and bark. Densely woven grass and bits of string form deep walls, making this a secure shelter for the eggs inside. At the bottom of the nest, the eggs are protected from wind, rain, and sun. Here, the parent oriole will spend much of her time sitting on the eggs, keeping them warm until they hatch. The downy woodpecker doesn't build a nest. This bird simply drills a hole in a dead tree and lays its eggs inside. The holes in the wood are small enough so that few other animals can get inside. So this home protects the woodpeckers from animal enemies. Food is found nearby, also in a tree. The woodpecker is listening for beetles and other insects beneath the bark. Many of the insects that woodpeckers eat are found in trees. The horned lark looks for its food on the ground. Its nest is also on the ground, hidden in the grass. It's important not to touch the eggs or the nest too much. If people disturb the eggs or the young of birds, the parents won't come back. The mother lark has returned. She will sit on her eggs, keeping them warm so they will hatch. The fledglings are quite helpless and almost always hungry. Finding food for them is a full-time job. The mother lark makes hundreds of trips each day, carrying insects to her family on the ground. Some of the nests that are most difficult to find are found in marsh areas, in the midst of reeds and other tall plants. Here, just above the water, is the home of a red-winged blackbird. The baby blackbirds are partially hidden from our view by the tall marsh plants, which also hide the birds from other animals. The nest is fastened to the tall plants with twisted strands of coarse grass. Finer grass is used in the inner lining of the nest, forming a soft, warm bed for the babies. Mother blackbird has the job of feeding the young ones. Another bird that lives in the marsh is the coot. It builds a nest that floats like a raft. Here, through tall marsh weeds, we see baby herons in their nest. This bird home was easy to make. The reeds have been simply pushed into a bowl-like shape. As soon as it is old enough to wade, the fledgling heron begins searching for fish and insects found in the water. Other birds that find their food in the water are these terns. Huge flocks of terns swarm along the seashore and on large lake beaches. Look carefully across the beach and you can see many eggs just resting in the sand. It seems strange to see the eggs out in the open like this. The sand doesn't seem to offer much protection. But the parent terns shelter the eggs with their bodies, and the whole flock will use their sharp beaks to attack any enemies who may venture too near. Even if the parents should leave the eggs for a while, they probably won't be bothered. Although the eggs are not in nests, each egg is camouflaged by its markings, which blend in with pebbles on the sand. That's why it's difficult to see the eggs from far away. On the side of a riverbank, we can find the homes of another kind of bird which lives near the water, the bank swallow. The holes in the side of the bank have been dug out by the swallows as places to hide their nests. Flocks of these birds are generally found living together in colonies. Each swallow family lives in one hole. The hole is the opening to a tunnel that goes back several feet into the soil where the nest is built. Both mother and father swallow sit on the eggs and care for their young. Another kind of swallow builds its home out of mud. Since it can only carry one droplet of mud at a time, the swallow must make hundreds of trips to build its home. Such nests are often attached to the sides of barns and abandoned buildings. Homes built by men have become the preferred nesting places of many birds. This house is no longer used by people, and neither is the chimney, so it makes a perfect shelter for another bird, the chimney swift. Look down deep inside the chimney, and you can see the nest of this bird. What a safe, secure place for the chimney swift to lay eggs and raise its young. Can you see how a hollow chimney is something like a hollow tree? Such trees are the natural homes of chimney swifts. Another bird that seeks out man-made structures for its home is the eastern phoebe. The phoebe builds a large nest of many different materials. Leaves, moss, hair, feathers, and mud are all worked together to make a well-protected home for the fledgling phoebes. This robin has built her home on a nesting shelf, which was made for her by Kathy and Steve, with a little help from their dad. They're very proud to have a robin nesting in their home. If you wish to build a home for a bird, you must decide what kind of bird it is for and make the home and entrance just the right size. If you've done a good job, birds such as this wren may set up housekeeping in the home you've built. A home made for purple martins is like an apartment house. It has many openings and a separate apartment for each nest. Building homes for birds and watching them build their nests can bring you enjoyment and can help you learn a lot about birds and how they live.
The color wasn't so bad on that, but it was definitely, when we scanned it, it definitely had faded some. Cornet, when they shot footage, they were using Kodachrome, which is a beautiful color film format that was discontinued by Kodak. But you could get beautiful color, and they would edit that, then they would print it to a cheaper color stock, which was usually Ektachrome or Aceman color, and that would fade over a period of time. So that's why we sometimes have beautiful footage and why sometimes we have meh footage. All right, let's learn about Belgium and the Netherlands, lands and their people. Oh, and thank you, Burrow Al, for the donation. That will support us and buy some coffee or pay for some shelving or pay for some one of the rental units. Thank you.
Belgium and the Netherlands are nations of many port cities. The harbors of these cities are crowded with ships being loaded and unloaded. The harbors are busy places of trade. Belgium and the Netherlands are also lands of many waterways, rivers and canals that are also used for trade. Water and trade are important to the Belgian and Dutch peoples, as we shall see. The Netherlands and Belgium are two of the smallest countries in north-central Europe. Together, the Netherlands and Belgium are a little larger than the state of West Virginia, about 27,000 square miles. Each of these dots represents 500,000 people, a total population of more than 20 million. How can so many people earn a living in these small countries? Here is one answer. The Netherlands and Belgium lie close to the great manufacturers of Europe, Great Britain, Germany, and France, and handle many products of these manufacturing nations. Do these rivers and the North Sea help make trade possible? Important rivers that flow out of France and Germany have their mouths in Belgium and the Netherlands. These rivers and their connecting canals play a major role in trade and transportation in the Netherlands and Belgium, sometimes called the Low Countries. In many places, the coast of the Netherlands is low, so low that rising waters of the sea could flood the land. To prevent this, high barriers called dikes have been built by the Dutch. The Netherlands and Belgium, then, are called low countries because land elevations are generally low. How has this affected farming? The farms of Belgium and the Netherlands are small and well kept. This Dutch farm belongs to Mynheer de Jong. He is telling his son about the potato harvest. Potatoes, as well as beets and turnips, produce a heavy yield per acre and are important food crops. In both countries, fine dairy cattle are raised on the low, moist pasture lands. Farmers have increased their pasture lands, especially in the Zuider Zee area, by reclaiming land from the sea. How is this done? First, a dike of concrete or stone is built. This keeps the sea waters from further flooding the area to be reclaimed. Then, in pumping stations like this, electric pumps drain the water from the area. The water is pumped into canals. Some windmills are still used to aid in pumping water from canals into the North Sea. The land reclaimed from underwater is called polder land. Dutch farmers use the flat, fertile polders for grazing and growing crops. Greenhouses are another way Dutch farmers use their limited land area. Inside the greenhouses, farmers grow fruits and vegetables in and out of season. Fine hothouse produce includes tomatoes, grown for domestic use as well as for export. Other exports are tulips and hyacinths, raised by Dutch farmers in the sandy soil of the coastal region. Some cut flowers are exported, but the main reason tulips and other flowers are raised is for their bulbs. After the plants flower, the bulbs are dug from the sandy soil. These bulbs are one of the chief exports to other nations. So bulb raising is an important industry. Other industries include the mining of some zinc and lead in Belgium. In both the Netherlands and Belgium, coal is the only plentiful mineral. In the coal mining areas, the people live in small villages. Most of the men here work in the mines from which thousands of tons of coal are taken every year. And here comes some of that coal. The Netherlands produces coal for domestic use, while Belgium produces enough low-grade coal for export. These containers of coal are being efficiently transferred by crane from the railroad cars to the familiar canal barges. The coal, dumped into the barges, is then transported along the busy canals to the larger cities of the Netherlands and Belgium. This barge is pulling into the harbor of Amsterdam with a cargo of coal. Other barges and ships bring commodities from all over the world. For Amsterdam and the cities of The Hague, Rotterdam, Antwerp, and Ghent are receiving centers for products and raw materials. Can you think of some reasons for this large volume of trade? Would access to the North Sea by the Netherlands and Belgium be one reason? During the age of exploration, Dutch and Belgian ships sailed through the North Sea and the English Channel to find trade routes to foreign lands. Today, Dutch and Belgian merchants continue to import goods from such overseas lands as Indonesia and the Belgian Congo. Mynheer Huizinga, an importer, is showing his son some of the sights of the harbor. They pass buildings along the docks where merchants trade in raw materials. They see raw materials that will be processed in Low Countries factories. These are sacks of coffee beans imported from Brazil. How are these imports used? The raw materials will go to manufacturing centers. Goods may be transported by barge or by rail to large manufacturing cities. Over long distances, when speed is necessary, air freight is used. For local transport, trucks are important in delivering raw materials to the factories. In some factories, raw cotton is processed for use in textiles. In others, steel is rolled for the large shipbuilding industry. Metals are also used in the manufacture of radios and other electrical goods. Diamonds from Africa are cut for jewelry and for use in industry. Raw foodstuffs, such as cocoa beans from Africa and South America, are processed and packaged for export. In addition to factories where products are processed and packaged, there are refining plants. This large oil refinery is near the port of Rotterdam. A large amount of coal, both domestic and imported, supplies abundant power for many factories, and a dense population supplies factory labor, making it possible for the Dutch and Belgian peoples to process imported goods. Finished exports are shipped from the port cities. On the return voyages, the ships will bring more raw materials for the factories. Some boats are bringing fish, one of the chief foods and exports of the Low Countries. Do all ships in the harbor belong to the Dutch and the Belgians? No. Some of the ships belong to other nations. Many are from Western Europe. Important rivers of trade, such as the Scheldt, the Meuse, and the Rhine, have their mouths in the Netherlands and Belgium. Will ships and barges from Germany have to pass through the Netherlands to reach the North Sea? Will ships from France pass through Belgium to reach the North Sea? The development of port cities illustrates once more the importance of water and trade in the Low Countries. In the Netherlands and Belgium, we have seen that water and trade are two important ideas of geography related to the lives of the people. How has water affected the geography of Belgium and the Netherlands? How have Dutch farmers used land that was once underwater? How is manufacturing related to supplies of coal and dense population? Most important, how have the people used their access to the North Sea in building trade and supplying jobs? Perhaps now you can tell why the Netherlands and Belgium are sometimes called the trading workshops of Europe.
So the color on that was not very good. Not very good at all. Oh well. So behind me I have a, let's see, right there, I have a film scanner and I have a film set up. And I'm hoping this is a film about manufacturing because that's what it's titled. It's Modern Manufacturing Command Performance. So I'm hoping there's a lot of assembly line footage. Fingers crossed, we'll see. All right. Enjoy. Wait, let me change this. I have to change the title. But here we go. Hold on. Hold on. Oh my gosh. Let me stop. Alright, it's not ready yet. Sorry. Let's watch Handel and his music, and then we'll get it up and running. Sorry.
We're listening to a march written by George Frederick Handel, often called Mr. Handel of London, for London is the city where he lived most of his life. And so, in London, we find many reminders of the composer. Here is his London home, St. Paul's Cathedral, where he worshipped, and St. James, the palace of his royal patrons. Royal and noble families were the main supporters of music during the 18th century. George Frederick Handel was perhaps one of the greatest composers patronized by 18th century nobility. The music of the time, Handel's music, reflected their noble, stately way of life, their classically styled homes, and their formal gardens. In some ways, the music of Handel can be compared to this formal 18th century garden. It is music with a definite pattern, symmetrical, evenly balanced. The pattern is a classic one, derived from ancient Greek and Roman models. To the classic pattern of music has been added a great deal of musical ornamentation, sweeping flourishes and intricate harmonies. This music, based on classical structure with added ornamentation, is called Baroque music. Handel's compositions are written in this Baroque style. A fondness for historical pageantry is another feature of the music of Handel. Listen to this noble passage from a composition called The Water Music, written for royalty. Such music expresses the color and pageantry of royal London. This music of pomp and ceremony is taken from a suite, a collection of short musical pieces. Handel used the classic ornamented Baroque style in many other musical forms. He used it in operas, based on classic Greek and Roman themes. Handel in the 18th century also used the Baroque style in the oratorio, a religious music drama based on biblical texts from the Old or New Testament. A third musical form with which Handel worked was the masque. The masque was a courtly entertainment, much like a pageant with accompanying music. Handel wrote in a variety of other musical forms: compositions for orchestra, recital pieces for solo instruments, cantatas, and many more. In all compositions,
melody was his chief concern. To understand the works of this composer, we must know something of his life, a life that began in Germany of the late 17th century. Even as a child, George Frederick loved to hear and play music, but his father frowned upon this interest. Father Handel lectured the boy. Music was a trade for peddlers and beggars, especially in Germany, where young Handel was born. In 1695, when Handel was about 8 years old, Germany was a collection of provinces or small kingdoms, each of which had its own capital city and monarch. Handel lived in the province of Saxony, in the town of Halle. Weissenfels was the town where the Duke of the province held court. On a visit to Weissenfels, young George, filled with excitement, accompanied Father Handel. At the court, he would hear music. Their trip took them through many 17th century German villages, where music was looked upon as frivolous. But for the German nobility, music was an essential part of court life. Arriving at Weissenfels, young Handel must have watched the courtiers and listened carefully to their elegant court music. Music such as he himself would later write. The Duke of Weissenfels asked that the child be presented at court. He had heard of the boy's great musical talents. The Duke was much impressed with the youngster. Despite the protests of Father Handel, the Duke insisted that he be allowed to provide for the boy's musical education. Finally, Father Handel agreed. Under experienced teachers, the boy, Handel, learned the fundamentals of classical composition. As the years passed, he learned to compose in the light, gay manner of France and in the heavier style of his native Germany. He wrote music for church and court. But on a trip to Hamburg, Handel discovered a new musical form. In Hamburg, opera was being performed by actors who, wearing splendid costumes and fine wigs, sang and enacted dramas set to music. In years to come, the singing actor and the opera would be raised to new heights by this composer. But young Handel had still a great deal to learn about vocal music. What better place to learn than Italy, home of vocal music for centuries? In the city of Florence, in palaces such as this, Italian music, music that was light and sunny, was being played. Handel adapted this Italian style to his own music, in compositions such as his delicate Italian cantatas. These cantatas mirror the spirit of Italy, still under the influence of the Renaissance, and blend beautifully with the art of this period. Having learned the Italian manner of composition, the composer left the courts of this country for the courts of his native Germany. Here at Hanover, Handel became chief musician to George, the Elector of Hanover, who was to become King of England and continue to be the composer's royal patron. Handel's life at Hanover was spent in teaching the children of the court and composing. Yet, the composer was restless. He desired to write operas, but there was no opera at Hanover. Where might he find the opportunity to fulfill his desire? London. 18th century London, a city of change, of expanding business activity, literary activity, and most important to Handel, expanding musical activity. London became his home. In this city, he lived and composed his music. First, there were operas. His home was often the scene of opera rehearsals as the composer accompanied his singers. Let's listen to a recitative from one of Handel's most famous operas, Julius Caesar. The words are sung in Italian.
Che bello, o numi, il mio bel sol qui dorme, vaga Lidia adorata, ah, se di tanto incendio che mi bolle nel seno ti penetrasse al cor qualche scintilla, ben potresti sperar dalla tua sorte d'essermi forse un dì sposa e consorte.
For years, Handel's operas in the Italian style were immensely popular. But by the 1730s, the composer was nearly bankrupt. The public no longer wanted classical Italian operas. Religious leaders had condemned Handel's staging of operas dealing with religious subjects. Was bankruptcy to be the end of this composer's musical career? Now, Handel worked feverishly on a different musical form, the form with which we associate his name today, the oratorio. The perfection of the oratorio, a dramatic story based on a biblical text and set to music without stage action, is one of the greatest contributions ever made to the world of music. It was the contribution of George Frederick Handel. Handel's reputation was restored with the composition of his first oratorio, Esther. Others followed, Saul, Judas Maccabeus, Israel in Egypt, and perhaps the most familiar and beloved of all oratorios, Messiah. The stirring solo arias and magnificent choruses of this great religious work appeal to all peoples of all nations and all times. Who of us does not respond to the reverent, joyful chorus of Hallelujah? Messiah is filled with majestic, graceful melody fashioned in the Baroque style. It is music that communicates quickly and to all. It is the music of a master composer, George Frederick Handel.
Woo! All right. Now, modern manufacturing command performance.
We must have modern manufacturing, as modern as we can make it. Modern manufacturing is a command performance.
Command performance. Well, we usually have enough command of our process to get the performance we want. Of course, it takes a lot of time to get from a set of new drawings to a finished product.
But time is something we don't always have. The period from development to product is growing shorter and shorter. As someone said, time has collapsed. Now let's try this. Say the complete product K, and we're changing it with a modification of the type XR. Now, suppose all you needed to do was to say into a transmitter 3 type 20K modification XR.
Orders to the plant.
That's right. You merely define what you want, and in a fraction of the time it would take conventionally, your product's manufactured, assembled, and ready to ship. And that component we were talking about is only one of many making up the complete product.
How could you do all that so quickly?
Not only so quickly, but in much less space. You'd need a much larger plant to do this by conventional methods.
Oh, this is not conventional.
Not at all. This is a modern plant. Really modern.
What do you mean by that?
When you give your command over the mic, which may be in the plant or remote, almost anywhere, the information feeds into a voice converter, which translates your language into a language which the computer can understand. The computer analyzes your request, then draws on its store of information to produce a series of tapes, which feed into a production control center. This center not only controls each of the machines, but the flow of parts as well, acting as a scheduling unit. Now all of the manufacturing units are actuated. Basic shapes are routed to production centers for complete processing. Completed components are then checked automatically by inspection machines, then sent on to a robot subassembler. Subassemblies proceed on to a robot for final assembly, and then on to shipping. That's what I call command performance. Of course, I've oversimplified the process a bit.
You mean you've been putting me on, don't you?
Not exactly. This is not as fantastic as you might think. Take the computer, for example. Computers are fairly common today, although we still must talk to them with cards or tape rather than directly. But they're getting more sophisticated all the time. And from this information, a control tape is produced.
Control tape for what?
To control a manufacturing process. Now these machines are in existence today. Inexpensive tape-controlled drill presses. The more sophisticated turret drill presses. Vertical turret lathes, capable of high accuracy contouring. Tape-controlled engine lathes. With equally exacting contouring and thread-cutting capabilities. high-precision multi-axis profiling mills. Machining centers that change tools, mill, drill, bore, ream, and tap. In many cases, they can complete the entire manufacturing process in just one setting. Fully capable of doing that job of yours we were talking about, and even more. Now, what different tools would you need for this piece?
6 different milling cutters, 4 sizes of drills, 4 reamers, 6 taps, and 4 boring bars.
And where you needed 8 machines to use these tools, the whole batch is loaded into a magazine for use by this one machine. All the instructions to the machine are on a punched tape. The intelligence on the tape tells the machine exactly what to do. This is called numerical control, which is one of the means of using mathematical definitions to furnish intelligence a machine can understand. There are many methods of accomplishing this. However it's done, it certainly shortens the chain of command and greatly reduces the opportunities for a breakdown in communications. There's the same casting you would have started with in your conventional shop. But notice there's only clamps required. The machine itself will even make its fixtures from tape control if necessary. And there you are. All the machining done in only 45 hours. How long would it have taken in your shop?
Oh, about 300 hours to machine and 26 weeks of lead time.
Half tooled up. Remember, the lead time here was only 2 weeks. If you need a second or third or fourth piece, you get them in a matter of hours. All exactly alike. Now that's performance.
What happened to automatic inspection you were dreaming about?
That was no dream. They're already in existence too. And research and development are making them better all the time. On this machine, a probe is guided by a tape similar to the one used in manufacturing the part. The measurements are recorded for inspection and record.
But you still need an original detailed drawing, don't you?
Not necessarily, but if you want one, it can be made from a numerical control tape too, operating an engineering machine. Often the drawing can be made at the same time the part is being made, using instructions from the same tape.
I notice the loading and removal from the machine is still conventional.
But it needn't be. You'll find automatic loaders and transfer mechanisms on a lot of production lines today. This automatic material handler remembers every sheet in its inventory and will deliver it undamaged in seconds. This robot manipulator will perform a variety of handling operations. It can be easily taught to load, unload, and assemble parts because of its electronic brain. So you see, we have practically all the elements of our plan of the future. It's just a matter of time before someone puts them all together to make the dream a reality. I don't know that anyone has ever produced a crystal ball on one of these machines, but you don't need to be a fortune teller to realize that our success in aerospace depends upon our national capability to produce combat-ready systems with complete reliability. We must produce first, best, and at the lowest possible costs, which are consistent with reliability and reproducibility. This means that we must be able to manufacture from all sorts of new and exotic materials. It means we must be able to produce structural members with a high degree of configuration complexity. It means we must produce with greater dimensional control. Some large rocket engine inducers, for example, can't be produced to design concept by conventional manufacturing methods. It means that we must produce components which have structural integrity. This aircraft bulkhead was built up of over 90 different parts, requiring more than 1,000 rivets and high-strength fasteners. You can imagine how long it took to tool, machine, and assemble all these parts. And you can imagine the possible human error involved. The more modern one-piece bulkheads have greater structural integrity, but they were still expensive. These one-piece bulkheads were first produced by conventional methods, using specially designed tracer-controlled rotary tables with many coordinated overlay templates and tracer patterns. It took 160 hours of machining time to produce one bulkhead, and at considerable cost. The part is now programmed on a numerically controlled skin mill to machine 2 at a time. This requires only 2 sets of vacuum chucks and 9 reels of tape. The time reduced to only 9 hours per part, and the cost reduced by 80%. In addition, there's a 25% reduction in weight. Command performance? I'll say. But you can best get it with numerically controlled machines.
Can this type of control be applied to other types of machines?
Certainly. There are machines that automatically position and punch all types of panels. Machines which build up rocket motor cases by the controlled winding of glass filament. Machines that position connector panels for wiring. Machines that position and make the wiring connections on assembled electrical panels.
machines for drilling printed circuit boards, machines for inserting the components in these boards, machines for spot welding, which saves 72% in labor costs. This machine has proved invaluable in spot welding fuselage sections. The more complex fusion welding also can be performed by numerical control. The tape not only controls the positioning and movement of the arc, but also the welding factors, gas flow, current, and the like. In guiding the arc, the control permits blind welding down through one structural member to fuse it with a hidden member below. The result? A stronger weld, a member with more structural integrity, a more reliable weapon system. Tubes can be bent by numerical control also. Tailpipes that fit any car precisely. Or the miles of plumbing used in modern missiles, and all without the need for separate jigs and setup time. By far the most versatile and flexible are the numerical controlled machines. For one-piece or production runs, they're the answer to involved machining operations. And for machining control, you can't beat instructions which are fixed and not subject to human error or emotion. Why, this tape could be sent anywhere in the world to a similar numerically controlled machine. And it would produce a part interchangeable with the one produced here from this tape.
May we backtrack a moment?
Surely.
Just how do the instructions get to the machine in the first place?
Well, let's begin with your own sketch of some part. Make it complicated. We'll hog it out of a block. Let's use master dimension.
Okay. There you are, with all the essential dimensions, but scarcely something a machinist could work from.
That took you about an hour. Now, we'll take this to a programmer as the next step in tape preparation. And there's the program. Now, let's see, that took about an hour and 45 minutes. Add that to the hour for the sketch.
And 5 minutes it took us to get here.
And the total's 2 hours and 50 minutes.
Those words on there look sort of familiar, but different.
That's right. They're a kind of pidgin English. This information will command the tool to start from the point called set point, which is defined as the point with coordinates 1, 1, 1. With the tool on the right, it is instructed to go right along the line base. At this point in the operation, the tool is sent forward to start cutting a previously defined circle about a previously defined point 2. Now here's that circle on the sketch. You can see it's a language that you can readily understand and use, and one the computer can understand too. As of now, conventional computers do not accept oral commands, so the instructions are put on punched cards or tape.
We're moving right along. Just 10 minutes for that job, for a total of about 3 hours. Now the computer operator gives the commands to the computer, which translates them into machine language. And here are the commands we'll take to the machine. We've now spent only 3 hours and 20 minutes. That's really chopping down lead time, isn't it?
Yes. I expect it would have taken me weeks to design and tool for this job.
It might be a good idea to think about modernizing then.
Mm-hmm. Now, this whole system's called numerical control?
Well, the machines are operated by numerical control. When you talk to a computer, though, well, that's a little higher order of communication. I suppose you might call it symbolic control at that point. But look, your part is already being manufactured. There's your part. Just 4 hours after you started making the sketch. You want to check it out?
You bet. Amazing. Absolutely amazing.
You see, what happened was that the machine did what machines can do best, and humans did what humans can do best. You did the designing, the creating. The programmer planned the process from his knowledge of machining and the particular machine. And being human, you were able to start a chain of command to the machine, a very short and very exact chain. As a result, you obtained a superior performance from the machine, far better than by conventional methods. And you get the same performance time after time, because the commands cannot change.
And that's why you call it command performance.
That's right.
Well, what about the actual joining, forming, or removal of metal? What's new along these lines?
Plenty. Electron beam welding, for one thing. Here, even two dissimilar metals can be permanently fused together by the high-velocity electron bombardment in its vacuum chamber. Electrolytic machining, for another. The cooling holes in this turbine blade were eroded to exacting tolerances by this stem drill. The hollow drill electrodes never touch the material, so they need not be reset or replaced.
Just the opposite of electroplating, huh?
Correct. This finished turbine bucket was shaped from high-temperature material. And here are the shaped electrodes that were used to do it. The process replaces a dozen conventional machines and produces a yearly savings of about 80%. When subjected to enough pressure, metals become plastic and are easily formed. This vertical shear forger produces turbine compressor shafts at a savings of $1,500 per part. Similar machines will turn out shapes such as cylinders, cones, and rocket motor cases from practically any metal, including many of the exotic alloys. Or suppose your product needs formed parts, like this. This machine pre-stresses metal to its yield point and has a tension control system, so that forming is accomplished with high accuracy.
This jet engine part was formed from Rene 41 in just 2 minutes, and the savings over conventional methods is 80%. A similar type of process will give you savings of up to 90% on drawn components like this, and permits the use of inexpensive dies. This blank holder, adapted to a conventional press, pre-stresses the metal and makes it more flowable than plastic. By adjusting the stress, almost any metal can be formed using the same die. Normally, 3 draws would be required to produce this part, with 270 hours of handwork for finishing. But here it is, produced in 1 stroke, holding its shape without springback and maintaining that shape throughout subsequent welding. This hydroform turns out complex shaped parts in seconds that formerly took hours to fabricate, assemble, and weld. The rubber bladder reduces tooling to only 1 inexpensive die. Want more savings in forming metals? Perhaps electromagnetic metal forming is the answer. This process uses powerful magnetic fields to swage, expand, compress, coin, shear, and assemble conductive metals without mechanical contact with the work. This machine uses the explosive power of man-made lightning to form parts.
What about forging?
How about that? That's high energy rate forging. These machines will deliver a terrific amount of energy in a split second to forge those as tungsten or even cast iron, as well as the usual materials. High-tonnage mechanical presses also offer great savings in the production of precision forgings. For testing electronic systems, there's automatic testing equipment. Here's a complete checkout of a wiring harness. This machine checks missiles, computers, systems, and the like. The results of the tests can be recorded on a printed readout. And the savings? Well, in addition to the time, this piece of equipment replaces 150 separate pieces of test equipment required on many of the complicated checkouts. Imagine what all these methods of modern manufacturing are going to do for the designers. And of course, you've seen only a few of the many new methods available today. No need for them to be limited by the restrictions of conventional manufacturing. They can now design a part to do the best job without compromise with manufacturing limitations. I doubt if there's a machinist in the world who could have turned out this part and met the required specifications. Yet it's a vital part. And I know that without modern machining, it could never have been produced in time to get our missiles in operation on schedule. And believe me, we must be on schedule in these areas. You know, today in some sections of the world, the smelting of iron is still a primitive process. And metal forming is equally crude. But some of our manufacturing processes still border on the primitive. While even the most modern standard machine tools are efficient for general applications, they will not readily accept the numerical control input, so vital for the effective production of aerospace vehicles. We must modernize our manufacturing methods and go from design concept to finished product as quickly as possible. We must keep the wheels turning the best way we know how. We must apply what we know today and search for ever better methods. This is a command performance for the survival of industry and our country.
Say, do you still have that clipboard?
Sure. Here it is. Why?
I want to write myself a note, so I won't forget something. See? This is going to be a command performance, too.
Good idea. Because the Defense Department expects its contractors to maintain a modern base in their facilities. In keeping with advance of aerospace technology, we need the productivity, reliability, and repeatability that only modern manufacturing can provide. And we all need the savings which can be effected in both time and...
Oop. Sorry about that. Where am I? Where am I? There I am. I was eating lunch, watching some beautiful machining footage. Beautiful. And there were some mentions of sex in the comments. Yeah, this is very sexual stuff. I consider this assembly line porn, in that it is obsessed. It's all this close-up footage. It's obsessed with making the product and not the product itself necessarily. And also there's great music. So there you go. That's my take on it. Don't say porn often on this channel, but assembly line porn. There you go. Thanks for tuning in today. We'll be back again live tomorrow. So one thing real quick. The Air Force seems so invested in all this technology and getting their manufacturers. This is made to be shown to manufacturers who they dealt with. So, like, what was the impetus behind it? I mean, I know that from an Air Force standpoint, they wanted cheaper products and they wanted a quicker turnaround time, blah, blah, blah. Consistency, manufacturing. But was there some manufacturer that was making some of this stuff that was like, hey, Air Force, you should convince all your suppliers to use this equipment? I don't know. It's kind of interesting. But anyways, thanks for tuning in. If you like what you saw, hit the thumbs up. Hit the like button. Go to ko-fi.com/avgeeks or patreon.com/avgeeks. Those are great ways to support us. Thanks so much. We will see you tomorrow. Everybody take care.